A tiny magnet effortlessly lifts a paperclip from your desk. This simple act defies the gravitational pull of our entire planet. The force that keeps you grounded, that holds the moon in orbit, is unbelievably feeble. Gravity, the most familiar force in our daily lives, is astronomically weaker than nature's other fundamental forces, and this video will guide you through the mind-bending theories scientists have proposed to solve this cosmic mystery. For decades, physicists have been baffled by this profound puzzle known as the hierarchy problem. How can a force that sculpts galaxies be so weak that a child's toy can overcome it? By the end, you will understand why this question is a gateway to the deepest secrets of the universe, from hidden dimensions to the very first moments of time. What does this fundamental weakness reveal about the true fabric of our reality? Our universe operates on just 4 fundamental rules. These are the 4 fundamental forces of nature. You have already met gravity, the architect of planets and galaxies. Then there is electromagnetism, the force behind light, electricity, and the very chemical bonds that hold your body together. It is the reason you do not fall through the floor. The third is the strong nuclear force, an immensely powerful but incredibly short-range glue that binds the nuclei of atoms, fighting a constant battle to hold positively charged protons together. Finally, the weak nuclear force, the subtle sculptor responsible for radioactive decay, the very process that powers the sun and heats the Earth's core. To grasp their power disparity, consider a single proton in the heart of an atom. The strong force that locks it in place is about 100 undecillion times stronger than the gravitational pull between that proton and another. 100 undecillion is a 1 followed by 38 zeros. If the strong force were the energy of a supernova, gravity would be less than a single spark. This staggering difference is the hierarchy problem, a gap in power so immense it cannot be a cosmic accident. It is a fundamental clue written into the laws of physics, demanding an explanation. So how do we even measure such an unimaginable gap in strength? The answer lies in a set of numbers physicists call coupling constants. Think of a coupling constant as a dial that controls the raw power of a force. For electromagnetism, that dial is set to a value of about 1/137. For gravity, however, the dial is set to a number so vanishingly small it is almost 0. The gravitational coupling constant is about 10 to the power of -39. This means gravity is roughly 10 trillion times weaker than the electromagnetic force. That is a 1 followed by 36 zeros. To wrap your mind around a number that vast, picture a child's refrigerator magnet. That tiny piece of decorated plastic can effortlessly hold a note against the refrigerator door. In doing so, it is overcoming the combined gravitational pull of our entire planet, all 6 sextillion tons of it, all pulling that note down. That is the daily, tangible reality of gravity's profound weakness. This is not just a mathematical oddity. It is a fundamental feature of our universe that makes life possible. If gravity were even slightly stronger relative to the other forces, its crushing power would overwhelm everything. Atoms could not form stable structures. Stars would collapse in on themselves almost instantly. The delicate balance of chemical reactions that build molecules would be snuffed out. Our very existence hinges on gravity being the quietest, most gentle whisper in the cosmic conversation. This profound weakness is a prerequisite for our existence. A universe with stronger gravity would be a terrifyingly short and violent place. Stars, the very furnaces that forge the elements of life, would collapse under their own weight in mere seconds. Their nuclear fires would be snuffed out almost instantly, leaving a cosmos dark and barren. Atoms themselves would be unstable, their delicate electron shells crushed by an overwhelming gravitational pull. The complex molecular structures that form planets, oceans, and living organisms could never assemble. Life, as we know it, would be an utter impossibility. This is not just a theoretical exercise. The precise value of gravity's weakness is written into the fabric of our reality, a non-negotiable constant that allows for a universe rich with structure and complexity. This is why the hierarchy problem is so much more than a physicist's puzzle. It is a direct challenge to our quest for a final theory, a single set of equations that unifies all the forces of nature. Any theory that claims to be a theory of everything must provide a compelling answer to this fundamental question. Why is gravity the quietest voice in the cosmic choir? The solution to this mystery may very well rewrite our origin story, revealing what happened in the first fleeting moments after the Big Bang, and perhaps even what lies beyond the edge of our observable universe. Yet this cosmic imbalance points to an even deeper mystery within the rules of physics themselves. Our most successful theory for describing the subatomic world is the Standard Model of particle physics. It is a masterpiece of human intellect, a framework that with breathtaking accuracy describes the behavior of three fundamental forces: electromagnetism, the strong force, and the weak force. It tells us that these forces are not action at a distance but are carried by tiny particles. The electromagnetic force is mediated by photons, the particles of light. The strong force is carried by gluons, which bind quarks together to form protons and neutrons. The weak force uses particles known as the W and Z bosons. The Standard Model has predicted the outcomes of countless experiments with astonishing precision, cementing our understanding of the quantum world. But it has one colossal, glaring omission: gravity. The force that shapes the universe on the grandest scales has no place in this otherwise spectacularly successful model. There is no particle within the Standard Model that carries the gravitational force. Physicists have proposed one, the graviton, but it remains entirely theoretical. When we try to apply the quantum rules of the Standard Model to gravity, the mathematics completely breaks down, producing nonsensical answers like infinities. This is more than a minor oversight. It is a fundamental schism in our understanding of reality. It tells us with absolute certainty that the Standard Model, for all its power, is an incomplete picture of the universe. There must be a deeper layer of physics, a theory that operates beyond our current models, waiting to be discovered. This is the frontier where scientists are forced to propose truly exotic ideas, theories that can finally unite the quantum world with the force of gravity and solve the mystery of its profound weakness. This missing piece of the puzzle has a name: the graviton. Just as the photon is the tiny particle responsible for carrying the electromagnetic force, physicists propose that the gravitational force must also have its own messenger particle. This theoretical particle, the graviton, would be the fundamental unit of gravity, transmitting its pull across the vast emptiness of space. To fit within the mathematical framework of quantum theory, the graviton is predicted to have some very specific properties. It would be massless like the photon, allowing it to travel at the speed of light and exert its influence across infinite distances. But there is a key difference: its spin. While photons have a spin of 1, gravitons are theorized to have a spin of 2. This unique property is what would give gravity its always attractive nature, unlike electromagnetism, which can both attract and repel. The graviton is the crucial bridge that could connect our understanding of the immense cosmos with the bizarre rules of the quantum world. Yet, finding it is perhaps the most daunting challenge in all of modern physics. The very reason for its existence, gravity's incredible weakness, is also the reason we may never detect one. Think about how faint gravity's signal is. When a star explodes in a galaxy far away, ripples in spacetime called gravitational waves travel across the universe. By the time they reach us, these ripples are so minuscule that they shift the fabric of reality by less than the width of an atomic nucleus. A single graviton, an individual packet of that force, would be immeasurably fainter. To have any hope of spotting one, we would need a detector so massive and sensitive it defies imagination. perhaps one that uses an entire star or even a planet as its sensor. This is not merely an engineering problem, it is a fundamental consequence of gravity's quiet voice in the cosmic conversation. The search for the graviton, therefore, pushes us to the absolute limits of science, forcing us to ask if some secrets of the universe are, by their very nature, meant to remain hidden. Perhaps the universe itself is hiding the answer in its very geometry. What if gravity is not weak at all, but merely diluted? This is the radical proposal of the extra dimensions hypothesis, a theory that suggests we are not living in a universe of only 3 spatial dimensions. The force of gravity, unlike the other forces, might be free to spread out into hidden, compact dimensions that are curled up so small we simply cannot perceive them. To understand this mind-bending idea, picture a garden hose stretching off into the distance. To a tiny ant crawling on its surface, the hose is a simple 2-dimensional world. It can only move forward or backward, left or right along the length of the hose. It has no concept of the 3rd dimension that wraps around the hose. Now imagine you pour a single drop of water onto the hose. From the ant's 2-dimensional perspective, that drop is a puddle that spreads out and quickly weakens, becoming a faint stain. But from our 3-dimensional perspective, we see the truth. The water is not just spreading along the length of the hose, it is also spreading around its full circular circumference. The force of that single drop is being diluted across an entire dimension the ant cannot even imagine. This is the core of the gravity leakage theory. In our universe, the electromagnetic force, the strong force, and the weak force might be like that ant, trapped on the surface of the hose, confined to our familiar 3 dimensions of space. Their strength is concentrated here. Gravity, however, could be like that drop of water. It is not confined. It is free to spread out, to leak into these extra, compact dimensions. What we perceive as an incredibly weak force is, in reality, a fundamental power that has been diluted across a much larger geometric reality. This idea was given a powerful mathematical form by physicists Arkani Hamed, Dimopoulos, and defy in what is known as the AD model. Their groundbreaking work proposed that these extra dimensions could be far larger than anyone had previously considered. Instead of being vanishingly small, they could be as large as a fraction of a millimeter. On the human scale, this is still tiny, but on the quantum scale, it is colossal. If true, this would fundamentally reshape our understanding of the universe's fabric. The reason we do not notice these dimensions in everyday life is that all the matter and forces we interact with, everything except gravity, are pinned to our 3-dimensional membrane or brain within a higher dimensional space called the bulk. Only gravity in this model can seep out into the bulk, its strength dissipating as it fills these hidden realms. This is why the gravitational pull between 2 objects in our world appears so feeble. Its true strength is not concentrated here with us, but is instead shared across a reality with more spatial dimensions than we can see. But what if gravity's weakness is a direct consequence of the fundamental ingredients of reality itself? This is the promise of string theory, one of the most ambitious frameworks ever conceived. It proposes a stunningly elegant idea that every single fundamental particle, from the smallest quark to the hypothetical graviton, is not a point-like dot, but an unimaginably tiny, vibrating loop or strand of energy, a string. The only difference between an electron and a photon, between the particle that carries gravity and the one that carries light, is the specific resonant frequency at which its string vibrates. Think of a single violin string. By itself, it can produce a vast range of notes, from a low, resonant hum to a high, piercing pitch. In string theory, the universe is a cosmic symphony composed of these fundamental strings. The electron is one note, the quark is another, and the graviton is yet another unique vibration in this grand composition. This elegant picture naturally demands a larger stage. For the mathematics of this vibrational symphony to work, It requires more than the three spatial dimensions we experience. String theory posits the existence of 6 or 7 extra spatial dimensions, all curled up and compactified on a scale trillions of times smaller than an atom. In this breathtaking vision, gravity is not leaking away. It is simply one particular vibration woven into the fabric of these higher dimensional strings. The theory's grandest ambition is to naturally unify all 4 fundamental forces, showing how they all emerge as different manifestations of this single, underlying vibrational reality. Yet this beautiful idea comes with a profound and puzzling consequence: the string landscape. The precise way these extra dimensions curl up and fold upon themselves is not unique. The mathematics of string theory does not point to one single universe, but to an almost unimaginable number of possible configurations, perhaps 10 to the power of 500 different versions. Each of these configurations corresponds to a universe with its own unique set of physical laws and constants, including its own specific strength for gravity. In this vast cosmic landscape, our universe is just one tiny patch, one particular arrangement where the strings vibrate in just the right way to produce the 4 forces we observe, with gravity being exceptionally weak. This leads us to a deeply controversial and philosophical idea, the anthropic principle. It suggests that the reason we find ourselves in a universe with such weak gravity is simple: it is a prerequisite for our existence. In the overwhelming majority of other possible universes in the landscape, gravity is too strong, or the nuclear forces are too weak, and stars, planets, and life never form. We do not observe those barren universes because there is no one there to observe them. Our presence here acts as a selection bias, forcing us to live in one of the rare, finely tuned pockets of reality where conditions are just right for complexity and life to emerge. The weakness of gravity, then, might not be a fundamental law demanding a deep explanation, but rather a cosmic coincidence, a fortunate roll of the dice in a multiverse of infinite possibilities. This idea of a cosmic lottery, however, feels deeply unsatisfying to many scientists. It raises a profound and contentious question: is the weakness of gravity a fundamental law of physics, or is it merely a necessary condition for our own existence? This is the core of the anthropic principle. In its simplest form, the weak anthropic principle is a statement of observational selection bias. It simply notes that we, as conscious observers, can only find ourselves in a universe capable of sustaining life. We could not possibly be having this conversation in a cosmos where gravity was so strong it crushed atoms at birth, or where the nuclear forces were too feeble to light the stars. Our very presence here acts as a filter, ensuring that the universe we measure is one uniquely suited for us. It is like a fish born in a pond wondering why the water is so perfectly wet. The water is not designed for the fish is designed for the water. In this view, gravity is weak for no deeper reason than that we are here to notice it. This logic becomes far more controversial in its stronger version. The strong anthropic principle goes beyond mere observation, suggesting that the universe must, in some sense, be tuned for the emergence of life. This interpretation veers into philosophical and even theological territory, implying a purpose or a design behind the cosmic constants. For many physicists, this is a step too far, a retreat from the quest for a true, fundamental explanation. They argue that accepting the anthropic principle as the final answer is a cop-out, a surrender that halts scientific progress. Why should we stop looking for a deeper, more elegant theory that predicts gravity's weakness from first principles? The debate is fierce. Proponents of the multiverse and the string landscape see the anthropic principle as an unavoidable consequence of a vast, possibly infinite reality. If countless universes exist with different physical laws, then of course we inhabit one of the rare habitable ones. There is no mystery to solve beyond that. Critics counter that this makes physics untestable and unscientific. How can we prove the existence of these other universes if they are forever beyond our reach? The controversy forces us to confront the very nature of science itself. Is our goal to find a single, beautiful equation that describes our universe, or are we simply inhabitants of a random, if fortunate, cosmic neighborhood? The answer to why gravity is so weak may ultimately depend on which of these paths you find more compelling. Another elegant solution whispers from the equations of particle physics, a concept of profound symmetry that could have stabilized the cosmic ledger. Supersymmetry proposes that for every known particle in the universe, from the humble electron to the quirky quark, there exists a hidden, super-heavy twin, a superpartner. In this perfectly balanced cosmic dance, every fermion, the building blocks of matter, would have a boson partner, a force carrier. Every boson would be matched with a fermion. This doubling of the cosmic cast is not just for aesthetic appeal, it serves a critical function. In the chaotic quantum world, the vacuum of empty space is not truly empty. It seethes with temporary particles flickering in and out of existence, and these virtual particles contribute what physicists call quantum corrections to the mass of particles like the Higgs boson. Without a balancing mechanism, these corrections would naturally drive the Higgs mass, and by extension the scale of the weak force, to an unimaginably high value, making gravity's relative weakness seem absurdly fine-tuned. The superpartners are the universe's built-in accountants. For every virtual particle that pushes the Higgs mass upward, its superpartner would provide an equal and opposite push downward. They would cancel each other out with perfect precision, naturally explaining why the weak force scale is so much lower than the Planck scale, and thus why gravity appears so feeble in comparison. For decades, this was the most promising and mathematically beautiful solution to the hierarchy problem. The entire physics community held its breath, waiting for the world's most powerful microscope, the Large Hadron Collider, to unveil this shadow world. The collider was designed to smash protons together at energies never before achieved, recreating conditions a fraction of a second after the Big Bang. The fervent hope was that this immense energy would be enough to conjure these superpartners into fleeting, observable existence, yet the detectors have remained silent. No clear, definitive signal of a supersymmetric particle has been found. The simplest, most elegant versions of supersymmetry, which predicted relatively light superpartners, are now severely constrained. The continued non-detection is a growing mystery, forcing physicists to consider more complex and contrived versions of the theory, where the superpartners are far heavier and more elusive. This silence from the quantum frontier deepens the puzzle. If nature truly adores this kind of symmetry, why is it hiding it so well? The hierarchy problem, instead of being solved, has become more profound and more mysterious than ever. This grand particle accelerator, buried deep beneath the border of France and Switzerland, is a cathedral of human curiosity. The Large Hadron Collider is our most powerful microscope, a 27-kilometer ring of superconducting magnets designed to smash protons together at velocities infinitely close to the speed of light. Within its cavernous detectors, these collisions recreate for a fleeting instant the conditions that existed less than a billionth of a second after the Big Bang. Scientists aimed this immense machine squarely at the hierarchy problem, hoping the fantastic energies of these collisions would force reality to reveal its hidden layers. The primary targets were the predicted particles of supersymmetry. If these superpartners existed, the tremendous energy of the colliding protons should have been more than enough to shake them loose from the quantum vacuum, leaving their distinctive signatures in the intricate data streams of detectors like ATLAS and CMS. Other teams searched for different clues, probing for evidence that gravity was leaking into extra dimensions. They looked for the telltale missing energy, a sign that gravitons or other particles were carrying momentum away into hidden realms. The scientific community waited with bated breath, expecting a new zoo of particles to emerge from the data, but the universe, it seems, had other plans. The detectors recorded trillions upon trillions of collisions, a monumental feat of data collection. Yet within that ocean of information, the signals for supersymmetry and large extra dimensions were nowhere to be found. The simplest and most elegant versions of these theories, the ones that offered a clean solution to the hierarchy problem, have been decisively ruled out. This great silence from the quantum frontier is one of the most significant and puzzling results in modern physics. It has forced a profound and humbling reassessment. The hierarchy problem is not yielding to our most direct assaults. The mystery of gravity's weakness has only deepened, pushing theorists to consider possibilities far more exotic and strange than anyone had previously imagined. This is not the end of the story, but a dramatic turning point in an ongoing cosmic detective story, where the absence of evidence is itself a powerful clue. This great silence from our most powerful experiments points to an even more profound layer of the mystery, one written not in particles but in the fabric of space itself. The weakness of gravity is intimately linked to the baffling nature of nothingness, to the energy of the vacuum. According to our best theories of the quantum world, empty space is not empty at all. It is a seething, chaotic foam, a constant frenzy of virtual particle pairs flickering into and out of existence. Every cubic centimeter of this so-called vacuum should be bursting with an unimaginable density of energy, a force pushing outwards with incredible strength. When we plug this theoretical energy into Einstein's equations for gravity, we get a number for the cosmological constant, a value that should be driving the expansion of the universe at a rate so ferocious that galaxies, stars, and even atoms would have been torn apart in the first instance of time. The calculated value is a 1 followed by 120 zeros. Yet, when we look out at the cosmos, when we measure the actual acceleration of the universe's expansion driven by dark energy, we find a number that is almost zero. Not just a little smaller, but 120 orders of magnitude smaller. This is the cosmological constant problem, and it is essentially the hierarchy problem in another form. Why is the energy of the vacuum, the weight of nothingness, so incredibly feeble? The staggering mismatch is the same puzzle of imbalance, only this time it is the energy of empty space that appears inexplicably weak compared to its predicted quantum strength. This is not a separate issue. The cosmological constant is gravity's response to the energy of the vacuum. A universe with a strong vacuum energy would have an equally powerful gravitational response, a crushing curvature that would warp reality beyond recognition. The fact that we live in a universe where both gravity and the vacuum energy are so perfectly, delicately weak is likely no coincidence. Any ultimate theory that explains why gravity is the faintest force must also account for why the universe is filled with a whisper of dark energy instead of a scream. The fate of the cosmos, its ultimate expansion into cold darkness, is tied directly to this fundamental question of weakness. Solving one of these profound puzzles may be the key that finally unlocks the other. This profound weakness at the smallest scales makes its absolute dominance on the largest scales all the more astonishing. While the other forces are busy with local affairs, building atoms and molecules, gravity is the only force that works across the unimaginable emptiness of intergalactic space. It never turns off and it never repels. This unique combination of being always attractive and having an infinite range allows gravity to perform a cosmic magic trick. It accumulates. The tiny, almost negligible tug between two specks of dust adds up. Billions of such tugs between countless stars slowly but inexorably pull entire galaxies into majestic spirals. A single proton's gravity is irrelevant, but the collective gravity of trillions upon trillions of protons in a star overcomes the outward pressure of nuclear fusion, forging elements in its core. This is the beautiful duality of gravity. On the quantum stage, it is a silent spectator, so weak it is drowned out by the vibrant dance of other forces. But on the cosmic stage, it is the master conductor, patiently orchestrating the grandest structures in the universe over billions of years. The other forces largely cancel themselves out. Positive and negative electric charges attract and repel, creating a balanced, neutral cosmos. The strong nuclear force is spent entirely within the tiny nucleus of an atom. Only gravity, with its singular, attractive nature, builds upon itself without limit. A child's magnet can defeat the gravity of a planet, but no magnet in the universe can defeat the combined gravity of a galaxy. This is why we find ourselves in a universe of delicate balance, where the same force that is too weak to hold a note on a refrigerator is powerful enough to bend the path of light itself around distant stars. Isaac Newton first gave gravity a mathematical voice, describing it as a universal force of attraction between any two objects with mass. His law was a triumph, predicting the motions of planets with breathtaking accuracy. Yet Newton himself was deeply troubled by his own theory. He could describe how gravity worked with his equations, but he had no explanation for how it worked. How could the sun reach out across 93 million miles of empty space and pull the Earth into orbit? This idea of action at a distance, a force acting instantly through a void, struck him as absurd. Centuries later, a young patent clerk named Albert Einstein would provide an answer so radical it shattered this classical picture. Einstein realized that gravity is not a force in the way we normally understand it. There is no invisible chain pulling the Earth around the sun. Instead, he proposed that mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Imagine a taut, stretched rubber sheet. This represents the fabric of spacetime. If you place a heavy bowling ball in the center, it creates a deep depression. Now roll a marble across the sheet. Instead of traveling in a straight line, the marble will spiral inward, orbiting the central mass as if pulled by a force. The marble is not being pulled, it is simply following the straightest possible path through a curved geometry. The bowling ball has warped the stage itself. This is the core of general relativity. The planets are not being pulled by the sun. They are simply following the geodesics, the natural contours, of a space-time dimpled by the sun's immense mass. This geometric description was a monumental leap. It perfectly explained anomalies in Mercury's orbit and famously predicted how starlight would bend around the sun, a prediction confirmed during a solar eclipse. But this beautiful new picture came with a profound cost. In general relativity, gravity is not a force that can be exchanged in little packets like other quantum forces. It is the dynamic geometry of the stage upon which the quantum actors perform. This created an almost insurmountable barrier to unification. How do you apply the quantum rules, which deal in probabilities and discrete particles, to the smooth, continuous fabric of spacetime? When physicists try, the mathematics produces infinities that cannot be removed. This is the fundamental schism, the clash between the smooth cosmic stage of Einstein and the frantic quantum dance that happens upon it. The hierarchy problem, the shocking weakness of gravity, is the most glaring symptom of this deep divide in the very laws of physics. This clash between the smooth stage of spacetime and the frantic quantum dance gives rise to the ultimate theoretical nightmare, the quantum gravity conundrum. When physicists attempt to treat gravity like the other quantum forces, applying the same mathematical rules, their calculations immediately spiral into nonsense. The problem has a technical name, renormalization. For the electromagnetic force or the strong nuclear force, this process is a well-practiced cleanup routine. The equations initially spit out annoying infinities, but physicists have developed clever mathematical tricks to sweep these infinities under the rug, allowing them to extract the finite, meaningful answers that perfectly match experimental results. It is like a chef who knows that a recipe will inevitably call for a pinch of salt to balance an overwhelming sweetness, a predictable adjustment. With gravity, this entire process fails catastrophically. The infinities that appear are not a minor annoyance, they are an unstoppable flood. There is no mathematical trick, no cosmic pinch of salt that can remove them. Every calculation for a simple gravitational interaction between two particles produces an answer of infinity, a result that is physically meaningless. This is not a flaw in the math, it is a screaming alarm that our understanding of reality is fundamentally broken at this intersection. The very tool we use to understand the quantum world is completely incompatible with Einstein's description of gravity. This forces a profound realization that the smooth, geometric fabric of spacetime as we know it must cease to exist at a certain scale. There must be a point where the stage itself becomes granular, a frothing sea of quantum uncertainty. This is the domain of the Planck scale. To grasp how small this scale is, consider an atom. Now, shrink that atom down to the size of a single proton within it. That proton is still astronomically large compared to the Planck length. The Planck length is about 1/trillionth of a trillionth of the size of that proton. It is the smallest possible unit of space that can have any physical meaning. At this unimaginable scale, the very concepts of here and there, before and after, break down. The energy required to probe such tiny distances is equally mind-boggling, a number known as the Planck energy. To reach it, we would need a particle accelerator not 27 kilometers wide, but roughly the size of our entire Milky Way galaxy. This is not an engineering challenge, it is a fundamental barrier written into the laws of physics itself. The energy concentration needed to see quantum gravity in action would be so immense it would likely collapse into a microscopic black hole, instantly ending the experiment. This is why testing theories of quantum gravity is, for now, nearly impossible. We are trying to understand the rules of a game being played in a stadium so small we cannot even see it, using tools that are cosmically too large and too weak to make a dent. The profound weakness of gravity is the very reason its quantum nature remains the final and most elusive secret of the universe. This elegant cosmic landscape of possibilities might be surrounded by an impenetrable swamp. String theory's vast collection of mathematically consistent universes, the landscape, is now thought to be bordered by a region physicists call the swampland. These are theories of particle physics that look perfectly reasonable on their own. They might even align with our standard model, but they suffer from a fatal flaw. They cannot be connected to a consistent theory of quantum gravity. They are islands of logic that are ultimately unstable, destined to sink into the swamp of mathematical inconsistency. A theory stuck in the swampland might seem to work for a while, but it would eventually produce paradoxes or break down completely, proving it was never a true description of reality in the first place. This distinction is not just academic, it provides a powerful new filter for judging which ideas are truly viable. The most intriguing swampland conjectures impose strict, non-negotiable conditions on the laws of physics. One prominent conjecture deals directly with the cosmological constant, that bafflingly small energy of the vacuum. It suggests that the value of dark energy cannot be zero, and it cannot be a fixed, immutable constant. Instead, for a theory to avoid the swampland, the dark energy must be dynamic, capable of changing over time. This would mean our universe's accelerated expansion is not a permanent feature but a phase. Another key conjecture states that the range of forces in nature must be limited. There cannot be what physicists call global symmetries that are perfect and absolute. Every symmetry must be tied to a force, a gauge symmetry that can be mediated by a particle. This has profound implications. If true, it means the universe has a fundamental aversion to perfection and permanence at the deepest level. How could this possibly help with our core mystery, the weakness of gravity? The swampland criteria act like a cosmic bouncer, rejecting any universe from the logical club of reality where the hierarchy problem is solved in an unnatural way. For instance, a universe where the vacuum energy is precisely zero for no reason would be kicked straight into the swampland. The fact that our universe has a small, but not zero, cosmological constant might be the only option that keeps it on the solid ground of the landscape. These constraints force the parameters of our reality into a very narrow corner, one that might naturally include a huge gap between the strength of gravity and the other forces. The extreme weakness of gravity and the faint whisper of dark energy might not be independent puzzles, but two sides of the same coin, both required to keep our universe from sinking into the swamp. This offers a new and thrilling possibility. Even if we never build a microscope powerful enough to see a vibrating string, we might still test string theory. We do this by checking if our own universe obeys the swampland's rules, by making incredibly precise measurements of how dark energy evolves over billions of years, or by searching for new, extremely weak forces that these conjectures predict must exist. We can look for the fingerprints of a consistent quantum gravity theory on the largest scales imaginable. The solution to the hierarchy problem may not come from finding a new particle, but from discovering that the cosmos itself is obeying a deeper set of architectural laws. Laws that demand gravity must be the quietest force in order for the universe to even exist. Perhaps the most dominant substance in the cosmos holds the key. Over 95% of the universe is made of dark matter and dark energy, two profound mysteries that we can only detect through their gravitational influence. Dark matter, an invisible scaffolding that holds galaxies together, feels gravity but ignores light and all other forces. Its ghostly presence is felt only through the way it tugs on stars and bends spacetime. This makes dark matter a unique cosmic probe. If dark matter particles truly interact with nothing but gravity, then studying them becomes a pure experiment in gravity's nature. Could dark matter be composed of particles that are themselves messengers from the realm of quantum gravity? Some theories suggest these particles, unlike anything in the standard model, could be streaming through this room right now, and their gravitational signature might reveal how gravity behaves at its most fundamental level. Detecting a dark matter particle would not just solve one cosmic mystery, it could provide the first direct look at how gravity couples to the quantum world. This invisible majority of matter might be a hidden portal, offering a clear view into the force that otherwise remains shrouded in weakness. On the other side of the cosmic ledger lies dark energy, the repulsive force accelerating the expansion of the universe. Its existence poses a question of balance. Could the apparent feebleness of gravity on our human scale be connected to this vast, repulsive push on the cosmic scale? It is a highly speculative idea, but some physicists wonder if dark energy acts as a kind of cosmic counterweight. On the grandest stages, the relentless outward push of dark energy might be subtly cancelling out some component of gravity's inward pull, making the force we measure locally appear even weaker than its true intrinsic strength. Think of a vast, invisible spring stretched throughout the vacuum of space, constantly pushing outward. This repulsive background might slightly offset gravity's attractive grip, contributing to the immense gap we observe between it and the other forces. While this is a long shot, it illustrates a beautiful and crucial point. The hierarchy problem is not an isolated puzzle for particle physicists. It is deeply woven into the greatest enigmas of cosmology. The invisible realms of dark matter and dark energy are not separate stories. They are different chapters in the same epic, a unified quest to understand why our universe is built with such a profound and necessary imbalance. The weakness of gravity might be the golden thread connecting them all. What if gravity itself is the shape-shifter? While most theories try to explain why gravity is weak, a small but persistent group of physicists asks a more radical question. What if our fundamental description of gravity is simply incorrect on the vast scales of galaxies? This idea challenges the entire premise of the hierarchy problem by suggesting that gravity is not a force that can be cleanly compared to its quantum cousins. Its apparent weakness might be a side effect of its behavior changing in different environments. The most famous of these alternative theories is known as modified Newtonian dynamics, or MND. Proposed in the early 1980s by physicist Mordechai Milgrom, MND starts with a stunningly simple observation. In the outer regions of spiral galaxies, stars orbit far too quickly for the visible matter present. According to Newton's laws, these stars should be flung away into the void. The mainstream solution is to invoke dark matter, an invisible halo of mass that provides the extra gravitational glue. But MND offers a different fix. Instead of adding invisible matter, it proposes a subtle alteration to how gravity works at extremely low accelerations, like those found in the faint outskirts of galaxies. Milgrom suggested that Newton's second law, force equals mass times acceleration, might need a tiny adjustment when accelerations become incredibly small. Below a certain threshold, gravity would become slightly stronger than Newton or Einstein predict. This single modification, with just one new constant, has a remarkable success rate. It can accurately predict the rotation curves of many galaxies using only their visible stars and gas without any need for dark matter. For its supporters, this is not a coincidence, but a sign that we are witnessing a new law of nature. Of course, a purely Newtonian adjustment is not enough. It must be integrated into a full relativistic framework, a theory of gravity that can compete with Einstein's general relativity. Over the years, several such theories have been developed, like tensor vector scalar gravity, or TVS. These frameworks attempt to build a modified gravity that works both for the solar system, where Einstein's theory is flawless, and for galaxies, where MND seems to have predictive power. This creates a fascinating philosophical split. The dark matter approach keeps our theories of gravity pristine and adds a new, mysterious substance to the universe. The MND approach keeps the mass budget of the universe simple and alters our theory of gravity itself. The implications for the hierarchy problem are profound. If MND or a similar theory is correct, then gravity is not a single, monolithic force with a constant strength. Its effective power could depend on the scale and the environment. The gravitational pull we measure in a lab on Earth, the basis for calling it weak, might be fundamentally different from the gravitational dynamics governing a galaxy. We are not comparing like with like. The other fundamental forces do not behave this way. Electromagnetism works the same in an atom as it does in a star. If gravity is inherently scale-dependent, then the entire exercise of comparing its coupling constant to the other forces becomes misleading, like comparing the speed of a single car to the average speed of all traffic. This is why the debate is so heated. It strikes at the heart of whether gravity is truly fundamental in the same way as the other forces, or if it is an emergent phenomenon, a collective behavior that arises from a deeper, more complex reality. While most of the physics community remains skeptical, largely due to evidence from colliding galaxy clusters that is very difficult for MND to explain, the theory refuses to fade away. It stands as a powerful reminder that our cosmic ledger is still open for revision, and that the final answer to gravity's mystery might require us to rewrite its very first principles. While our largest experiments have not found supersymmetry, other radical ideas were waiting in the wings, ready to challenge the very nature of the particles we thought we knew. One such path abandons the idea of a fundamental Higgs boson entirely. This is the world of technicolor and composite models. In this bold vision, the Higgs is not an elementary particle at all, but a composite object, much like a proton is not fundamental but is made of smaller quarks. The theory proposes a whole new sector of the universe, populated by unknown particles called technephomeons. These technephomeons would interact via a new, powerful force, a sort of super-strong version of the nuclear force that binds quarks. In the hot, early universe, this techne-force would cause technephomeons to bind together, and this process of condensation would dynamically generate mass for all the other particles, doing the job of the Higgs mechanism without needing a fundamental Higgs particle at all. The beauty of this approach lies in its naturalness. The vast difference in scale between the weak force and gravity would not be a bizarre accident requiring fine-tuning. Instead, it would emerge organically from the dynamics of this new, strong interaction, much like the mass of a proton emerges naturally from the frantic interactions of the quarks inside it. It offered a way to solve the hierarchy problem by removing the need for a delicate balance altogether. For a time, this was a compelling alternative. Yet, the same machine that searched for supersymmetry, the Large Hadron Collider, also delivered a verdict on Technicolor. In 2012, it announced the discovery of the Higgs boson, a particle that looked, for all intents and purposes, like the simple, fundamental Higgs predicted by the Standard Model. The properties measured so far, its mass and the way it interacts with other particles, have severely constrained the simplest versions of Technicolor. The data prefers a universe with a fundamental Higgs, not a composite one, so these models for now have retreated from the spotlight, but they have not vanished. They remain a vital part of the theoretical landscape, a testament to the incredible creativity physicists must employ when nature refuses to follow our most elegant guesses. Their legacy is a reminder that the path to quantum gravity may require us to dismantle even our most cherished assumptions about what a fundamental particle truly is. The silence of the Large Hadron Collider is not an ending, but a call to build even bigger ears. The next generation of experiments is already on the drawing board, designed to listen for the faintest whispers of an answer. One audacious proposal is the Future Circular Collider. Imagine a new underground ring, not 27, but over 90 kilometers long, circling beneath the European landscape. This colossal machine would slam particles together with energies up to 7 times greater than the LHC can achieve. The goal is not just to find new particles, but to scrutinize the one we have, the Higgs boson, with microscopic precision. By studying trillions of Higgs decays, physicists hope to spot tiny, statistically significant deviations from the Standard Model's predictions. Such a subtle anomaly would be a crack in the foundation, a sign that the Higgs is interacting with something we cannot yet see, perhaps the hidden particles of a more complex theory that naturally explains gravity's feebleness. But the quest does not rely on colossal machines alone. On a much smaller yet equally profound scale, other experiments are hunting for gravity's secrets not in high-energy chaos, but in the quiet void of extreme precision. These setups search for deviations from Newton's famous inverse square law at distances smaller than the width of a human hair. The logic is brilliant in its simplicity. If gravity is leaking into extra dimensions, its strength should not follow the textbook rules perfectly at microscopic scales. As you bring two exquisitely crafted masses closer and closer together, the gravitational pull between them should become slightly stronger than expected, as you begin to probe a regime where the force has not yet fully diluted into the hidden dimensions. To detect this, scientists use devices of breathtaking sensitivity. A torsion balance suspends a minuscule, pendulum-like mass on an incredibly thin fiber, shielded from all vibrations and electromagnetic influences. They then move another mass precisely nearby, looking for an almost imperceptible twist in the fiber, a twist that would betray gravity's true, concentrated strength. Another method, atom interferometry, uses the wave-like nature of atoms themselves. By dropping clouds of ultra-cold atoms and splitting them with laser pulses, they create an exquisitely sensitive ruler that can measure the subtle acceleration due to gravity from a nearby test mass. The movement of the test mass creates a tiny shift in the quantum interference pattern of the atoms, a shift that reveals the force's strength with atomic-scale resolution. Finding even the smallest deviation in these experiments would be a revolutionary discovery, a direct signal from the hidden architecture of spacetime itself. It would tell us that the universe is indeed woven from more threads than we can see, and that gravity's quiet voice is merely an echo from a larger, multidimensional room. The faint afterglow of creation itself offers another way to peer into this mystery. We can rewind the cosmic clock to its very first moments, a time when the universe was so unimaginably hot and dense that all four fundamental forces were likely merged into a single, unified power. This primordial era provides a unique laboratory, one where the energies were so extreme they could force gravity to reveal its quantum secrets. We cannot build a particle accelerator that powerful, but we can observe the relic it left behind. This relic is the cosmic microwave background radiation, a faint, cold light that permeates all of space. It is the cooled and stretched remnant of the universe's first flash, a baby picture of the cosmos when it was just 380,000 years old. Embedded in this ancient light are tiny, random variations in temperature, patterns of hot and cold spots smaller than 1 part in 100,000. These minute fluctuations are a frozen record of the violent quantum jitters that were magnified to cosmic size during a period of hyper-expansion called inflation. They are the seeds from which all galaxy clusters and vast cosmic voids would eventually grow. By mapping these patterns with exquisite precision using space telescopes and ground-based observatories, cosmologists are essentially decoding a message from the universe's infancy. The specific statistical signature of these fluctuations can tell us about the physics that operated at energies 1 trillion times higher than the Large Hadron Collider can reach. They can reveal whether inflation was driven by a single field or if more complex dynamics were at play, dynamics that might naturally explain the vast gap between gravity and the other forces. But there is an even more pristine signal hidden within this ancient light, one that has yet to be found. Theorists predict that the violent birth of spacetime during inflation should have sent powerful ripples through the fabric of the cosmos, primordial gravitational waves. Unlike the gravitational waves we detect from colliding black holes, these primordial ripples would have a unique signature, imprinting a distinctive swirly pattern known as B-modes onto the polarization of the cosmic microwave background. Finding this pattern would be like discovering the fossilized footprint of a quantum gravity process. It would be direct, observational proof of gravity behaving as a quantum field in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. A new generation of observatories is now aiming to capture this holy grail of cosmology. Projects like the LightBird satellite and ground-based telescopes at the South Pole are being built with unprecedented sensitivity, designed to scan the entire sky for the faint, swirling whisper of these primordial waves. If they succeed, the detection would not just confirm a key prediction of inflation, it would open a window into the epoch of unification, showing us a time when gravity was not the weak, solitary force we know today, but an equal partner in a single supreme law. This cosmic lottery forces us to confront a humbling possibility about our own significance. If our universe is but one accidental bubble in an infinite multiverse, then the laws we hold as sacred are merely local bylaws. The profound weakness of gravity, so essential to our existence, might be a random fluke with no deeper meaning. This shifts our place from the center of a designed cosmos to a fortunate outlier in a vast, indifferent ensemble of realities. It is a philosophical earthquake that resonates far beyond the lecture hall, challenging our deepest intuitions about purpose and design. Yet, this very uncertainty has become a powerful muse. The awe inspired by such a profound mystery fuels a creative explosion across our culture. Science fiction films depict travelers navigating hidden dimensions, while novels explore the emotional weight of infinite parallel lives. Artists create stunning visualizations of cosmic inflation and the string landscape, translating abstract mathematics into visceral experiences of color and form. These are not mere entertainment, they are humanity's way of wrestling with concepts too vast for equations alone. They give form to our collective curiosity and our deep-seated need to find a story within the staggering scales of modern physics. This puzzle captivates us because it sits at the precipice of the known, It asks the most fundamental questions we can pose. Why is there something rather than nothing? And why is that something arranged in this precise, life-allowing way? The hierarchy problem is more than a technical challenge for physicists. It is a mirror reflecting our eternal desire to understand our own home, a single, fragile data point in a cosmos of unimaginable scope. We often hear that gravity is leaking away into other dimensions, but this is a subtle misunderstanding of the theory. Gravity is not losing energy like a battery running down, nor is its fundamental strength changing over time. The idea is that its power is spread thin, diluted across a reality with more spatial dimensions than we can see. Picture a single drop of ink falling onto a small, dense sponge. The sponge soaks up the ink, and from your perspective, the vibrant color seems to vanish. The ink has not been destroyed. Its pigment molecules are simply dispersed throughout the entire volume of the sponge, becoming too faint to see. In this analogy, our three-dimensional universe is the surface of the sponge, and the hidden, compact dimensions are its inner structure. The strength of gravity is like that ink, present everywhere but appearing incredibly faint from our limited point of view. Its fundamental coupling constant remains the same, but its effective power in our world is minuscule because it is shared across a much larger geometric realm. This is a static feature of the universe's architecture, not a dynamic process of energy loss. Another common misconception is that we can be shielded from gravity, just as a metal cage can shield you from an electric field. This is not possible. Gravity, as described by Einstein, is the curvature of spacetime itself. You cannot block the stage upon which you stand. An object's mass warps the spacetime around it, and everything within that warped geometry feels the effect. There is no gravitational equivalent of a positive or negative charge that can create a protective barrier. If you were inside a hollow sphere, you would be weightless not because gravity is blocked, but because the gravitational pull from all parts of the sphere cancels out perfectly at the center. You are still deep within the gravitational well of the sphere and the Earth. You are simply in a state of freefall within that well. This absolute, all-pervading nature is precisely what makes gravity so unique and its profound weakness so baffling. It is always on, it always attracts, and there is no hiding from it, yet its signal is the quietest whisper in the universe. Clarifying these points is crucial because the true mystery is not that gravity is fading or that we have found a way to avoid it. The puzzle is why this fundamental, inescapable force, the very shape of reality, is so immeasurably feeble compared to the other forces that build our world. So where does this leave us in our quest? The landscape of possible answers is richer and more varied than ever before, yet the central mystery stands untouched. We have explored a universe where gravity leaks into hidden dimensions, where every particle has a super-heavy twin, and where the cosmos is one of countless bubbles in a vast multiverse. We have seen our most powerful machine return empty-handed, and we have heard the whispers from the cosmic microwave background. The undeniable conclusion is that we still do not know why gravity is so weak. This is not a failure of science, but a testament to the depth of the question itself. The hierarchy problem remains one of the most profound puzzles in all of physics, a wide-open frontier. This healthy state of debate, with multiple competing ideas all vying for validation, is precisely what makes this field so electrifying. There is no single path to follow, no dogma to obey. The next breakthrough could come from a colossal new collider, a tabletop experiment detecting a subtle deviation, or a telescope capturing a primordial ripple in spacetime. For the next generation of scientists, this unresolved mystery is an invitation. It is a call to look deeper, to think more creatively, and to challenge the very foundations of our understanding. The greatest discoveries in physics have always come from staring into the unknown and refusing to look away. The weakness of gravity is our universe's most persistent and elegant riddle, waiting for its solution. Gravity is the silent, pervasive force that sculpts the cosmos, yet it remains the faintest whisper in nature's conversation. We have journeyed from the baffling power of a child's magnet to the colossal silence of the Large Hadron Collider, exploring a landscape of mind-bending possibilities. We have witnessed how the elegant proposal of supersymmetry awaits its missing partners, and how the radical idea of extra dimensions suggests gravity's strength is simply spread thin across hidden folds in reality. We have even confronted the philosophical shock of the multiverse, where our universe's gentle gravity might be nothing more than a fortunate cosmic accident. The experimental hunt continues on all fronts, from colossal particle rings to tabletop experiments seeking whispers of deviation, and telescopes scanning the ancient sky for primordial ripples. This is not a story with an ending, but a living, breathing mystery at the very frontier of human knowledge. It reminds us that some of the simplest questions, like why we do not fall through the floor, can lead to the very edges of understanding. So what do you think is the answer? Does the idea of hidden dimensions resonate with you, or do you believe the multiverse holds the key? Share your favorite theory in the comments below. I am genuinely curious to hear your thoughts. If you enjoyed this deep dive into the fabric of reality, make sure to subscribe for more journeys into the universe's greatest mysteries.